When we talked last time about Newton's universal law of gravitation, we briefly mentioned center of mass, and that we do it from the center of mass of an object. It's also possible to calculate center of mass of a system. So like if we have mass 1 over here and mass 2 over there, and there's some distance r between them, we can calculate where the center of that mass is that system is going to work around. If these two objects are the same mass, it's fairly easy. Your center of mass, right, is going to be towards the center. Let's say if mass 2 were more massive, the center of mass would shift closer to mass 2. So for example, when we talk about having the sun right here and the Earth orbiting around the sun, so there's Earth's orbit, the center of mass of those two things isn't in either the sun or the Earth. It's just, slightly outside, maybe even just slightly inside the sun in this case, and closer to the sun because the sun is more massive. So when we talk about things orbiting in different ways, we're talking about them orbiting around the center of mass of the system rather than just one object. So it's kind of a good idea to know what center of mass is and just be able to roughly guess where it should be. So Kepler came up with 3 laws of planetary motion to describe how planets move. The first law is that objects orbit in an ellipse. So it's an elliptical path that objects orbit on, and so it looks something like this. So here we can see our elliptical path. With an ellipse, in physics, in math too, you have 2 foci, or a focus 1 and focus 2, and your object orbits around that. The sun, or whatever the object's orbiting around, is at one focus, and then the other one is just empty, there's nothing there. And then the planet orbits in an elliptical rather than a circular path. And to varying degrees of what we call eccentricity, sort of how squished that ellipse is, how little it resembles a circle, if you will. Some orbits may look, like this and be way out there. Some, like the Earth's, are actually pretty close to a circle. This is actually a little exaggerated. And so different objects sort of have it differently, but they're all in an elliptical path rather than being perfectly circular. Kepler's second law of planetary motion is that we sweep out equal areas in equal time. So what that means, if we look at the picture here, is that it would take the same amount of time to get from A to B as it does C to D and E to F. So it's an equal amount of time that's elapsed through each one of those intervals. And if you measure the area that's sort of swept out between those two, going back to the point they were orbiting around, those areas would all be equal in magnitude. So that kind of means that when we're closer to the planet, we're moving faster, which makes sense when we think about Newton's universal gravitation, right, over r squared. So if we have a smaller r, a bigger force, we're probably going to move around faster. And here we're further away, so we're going to move a little slower. So we move a little slower, but we're further away, so it's kind of this long, narrow area. Or we move fast, we cover a larger distance here, but there's this short distance away. So these two areas are actually the same. Newton's third law is kind of a mathematical proportionality. So we'll write it out here. So third law says that t squared for a planet is proportional to r cubed. Or another way of writing that would be that time for planet 1 squared over time for planet 2 squared, whatever you call planet 1 and 2, is equal to r1 cubed over r2 cubed. So if you knew the period of an orbit, so capital T is period, and r is the average distance between the planet, whatever it's orbiting, so let's say Earth and Sun and maybe Mars and the Sun. So if you know the period of the Earth, and you know how far away it is, and you know maybe how far away Mars is, you could figure out how long it takes it to complete in orbit. So it's just a nice little ratio that's kind of useful. If you know information about one planet, you can find information about the other. And it turns out that all planets, in fact all things that orbit, have this relationship.